Yeah, right. So up to now we have discussed about the lenses, types of lenses, and when a parallel beam of light passes through any lens, how does it deviate? Either will it deviate or converge. We came to know that when a parallel beam of light passes parallel to the principal axis through biconvex lens, that means this is biconvex lens, principal axis, and parallel beam of light. When it is passes parallel beam of light, what will happen? They will converge at a point, right? Converge at a point. So this is called biconvex lens. At the same time, when a parallel beam of light is converging at a point, we can name it as a converging lens. Okay. So now, this is the case where the parallel beam of light is parallel to principal axis. Now, the second case, if you observe, this is the biconvex lens, right? Biconvex lens, and it is a principal axis. Here, think it is F2 and it is F1, focal point. Now, see, parallel beam of light. See what it is? Parallel beam of light. What is the difference between these two cases? Here, parallel beam of light is inciding on the biconvex lens parallel to the principal axis. But here, in this condition, if you observe carefully, the parallel beam of light is incidenting on the lens by making certain angle with the principal axis. In this case, so here it is very clear. They will meet at a point which is known as focal length or focal point. Okay, focal point. But coming in this condition, here also they all will converge at a point. Okay. In this case also, all the parallel beam of light after refraction through biconvex lens, they will converge at a point which lies in the focal plane. See, right? This is the plane, focal plane. In this focal plane, they are meeting. Clear? So you must remember this point. So the parallel beam of light, definitely it will converge. That converging point must be in focal plane. If you draw from that side, in this focal plane it will mix. Okay na? This is for biconvex lens. Now let us see what will happen in the case of biconcave, right? Before what happened, when I draw parallel beam of light, they all diverge. If I extend them back, they met at a point which is known as focal point. Clear? Now let us see same lens, biconcave lens and principal axis. Now let me draw it like this. Clear? Parallel beam of light. This is parallel beam of light because the light rays are parallel to each other, but they are incidenting on the lens, making certain angle with the principal axis. They are not parallel with the principal axis, but this is parallel beam of light, right? So this parallel beam of light is incidenting on the lens, right? So now what will happen? In which see, this is focal point F2, and this is, let us take somewhere, here it is focal point F1, right? They must diverge, right? They must diverge. So they also will diverge like this. Sorry. Now let us see. they diverge. They diverge like this, right? So they are diverging. If you extend the back those diverging rays, ఈ refracted rays ని వెనక్కి extend చేస్తే they all meet at a point nothing but focal, right? Or else it looks very clumsy to you. Let me draw once again. See, let us take concave by concave principal axis. See, parallel beam of light, right? What they happen, they will think it is the focal point. It is the focal point. Now what will happen, they will diverge. If I extend it, it comes back like this. This is also diverge. If I extend it, it comes back like this. This is also will diverge. If I extend it, it comes back like this. It is also diverge like this. If I extend it, it comes back like this. It is also will diverge. If it comes back like this. See, every light ray is diverging. If I extend those divergent light rays to back, they are meeting at this point, right? See, this is coming here, this is coming to here, this is also coming to here, this is also coming to here. So they are meeting at a point which lies in the focal plane. Focal plane. It's very important. Based on this, you can solve a few problems in coming session, right? So this is about the beam of light when it making an angle with the principal axis. How does it behave, and where they appears to be meet or where they meet directly. If it is biconvex lens, they meet directly. If it is biconcave, then they appear to meet at a point because we are extending them back. That is the main difference that you have to remember. Now let us draw ray diagrams. Few ray diagrams. Ray diagrams in the sense we are taking a single light ray and we observe its path after refraction through any lens, right? So by using those ray diagrams, we'll easily trace the image where does it form. Okay. Now let us see. Let us take convex lens by convex lens principal axis, right? So this is f2, f1, 2f1 and 2f2. When a light ray passes parallel to principal axis, right? The light ray passes parallel to principal axis, it will passes through focal point. This is the first ray diagram. Clear? And the second light ray. When a light ray passes through focal point, okay? When a light ray passes through focal point, it will refract, it will move parallel to the, sorry, I don't draw here, I will draw separate lens once again. Okay, this is our first light ray, and second, again say convex, biconvex, and f2, f1, 2f1 and 2f2. Now when a light ray passes through focal point, then what will happen? After refraction, it passes parallel to the principal axis. Clear? The first light ray, which is parallel to principal axis, after refraction it passes through focal point. And the second light ray, when light ray passes through focal point, after refraction it passes parallel to the principal axis. And third one is say f1, sorry, f2, f1. Here 2f2, here it is 2f1. Clear? In the second case, when a light ray passes through optic center, it's never deviate. It undeviated and move forward. Remember that when a light ray passes through optic center, or else when a light ray passes through principal axis, they never undeviate. Okay, they undeviate and they move forward. Clear? They don't deviate. It continues its original path. But when they are making an angle or a parallel like this, they will deviate. These are the ray diagrams for the convex lens. You can draw same lines for the concave, biconcave. For example, this is a biconcave principal axis, right? This is F1 and 2F1, F2 and 2F2. Now, when a parallel beam of light passes through principal axis, parallel to the principal axis, I mean a light ray passing parallel to the principal axis and incident on the lens, then what will happen? It will diverge, right? You know already. So it will diverge such a manner that if we extend it back, it appears like coming from the focus point. Clear? After refraction through the biconcave lens, this light ray diverge such a way that it behaves like it is coming from the focal point. Clear? This is the first light ray. For second, let us see. If I draw a second light ray, same principal axis, and it is F1, F2, 2F1 and 2F2. When a light ray passes through focal point, okay, when a light ray passes through focal point, very simple, it will be parallel to principal axis. It will be parallel to principal axis. And same here also, in biconcave also, same thing. When a light ray passes the optic center, they never deviate, they undeviate. If they continue their path. So these are called ray diagrams. So this is the nature of light. We are observing the nature of light, how it is traveling. Right? So why these are? These are very helpful to trace the image. Clear? So now let us see how can we trace the image. Let me have a chalk piece. Yeah. Right? We have drawn the ray diagrams. Now let us see how does image form according to the position of object. Okay, right? In the first case, we'll draw with we take example of convex lens, biconvex lens. Okay, so now let us see in the first case, if the object is at infinite, if the object is at infinite, that in the sense nothing but let us see. So F2, F1, 2F1, right? So now object is at somewhere at infinite. Object at infinite. So when the object is at infinite, that means the light rays which are coming from the object, they are parallel to principal axis. You must remember it, right? So they parallel to principal axis, right? So we know that when a light rays are parallel to principal axis, they will meet at a focal point. So another light ray comes like this, and this also meet here. So what happened now? After refraction of the incident light rays which are coming from the object, they all are meeting at a focal point. That means the image is forming at a focal point, and it's a point size image, diminished. It's a diminished, and when the object is at infinite, the image will be formed at a focal point size image. Clear? Right? This is the, see here, by using light ray diagrams, we are tracing the image position with respect to the object position. Right? So next, in the second case, if you keep the object at a focal point, right? So now, sorry, this is the first condition. The first condition, where is the object? Object is at infinite. In the second condition, we will take object from far and we will keep it on the, right? Now this is the object. Let you think it is a candy. Right? Now the object is at center of curvature. Center of curvature. Now let us see how does image form. First light ray, which is, let us take a light ray. I mean, many n number of light rays are coming from the object, but we don't take all. We will take only one light ray. Right? So a light ray which is parallel to principal axis. It passes to focal point. We discussed already, right? When a light ray is parallel to principal axis, it passes to focal point. And next, a light ray which is passes through focal point. I am taking another light ray which is coming from the tip of the flame, right? So this is another light ray. After what will happen? The light ray which is passes through optic center, focal point. After refraction, it will be parallel to principal axis. So it is parallel. See now, the two refracted rays are meeting at this point. That means the image of this object will be formed here. See, this is where 2f1, right? Same size image will be formed. When the object is placed at center of curvature of the lens, then its image will be formed at another center of curvature of the lens, another side. Clear? Another side it will be formed, and here the same size image will be, okay, and it is a real image. If you place any screen like a white paper, if you place any screen here, then you are able to see this image, or else you cannot, because it is not a virtual image. Virtual image in the sense you can see your face in the mirror, right? That is called virtual image. But here it is a real image. It is a real image. You cannot see with your naked eye. If you place screen here, then you can see it. Okay. Here, when the object is at center of curvature, image will be formed at another center of curvature of the lens, right? And the image is a real image, and it is inverted. Okay, it is inverted and as same size of the image object. Clear? This is the second condition. Now, in third condition, let us see the third condition. In third condition, same, we'll take the convex and optic center f2, f1, 2f1 and 2f2. Now, in this condition, you place the object between the focal point and center of curvature, between the f2 and 2f2. Now again, let's draw ray diagrams for it. A first light ray which is parallel to principal axis, it passes through focal point, and which is passes through, let me extend in the mirror, I mean lens, right? So when it passes through it, what will happen? It will the light ray which is passes through focal point. Clear? Then what will happen? It passes parallel to principal axis. See, here it is forward. If I draw another light ray, see, the first light ray which is parallel to principal axis, after refraction passing through focal point. Second light ray which is passing through focal point, after refraction passing parallel to the principal axis. And third light ray which is passes through optic center, it does not deviate, so straight. They met at this point. These light rays are coming from tip of the candle, so the tip of the image will be formed here. That means clear. So if you want to draw clearly, sorry for it. Yes, exactly like this. See, this is object. So by using ray diagram, I traced the image. If you observe here, when the object is between the focal point and center of curvature, image also formed between the focal point and the center of curvature of another side. And it is a real image. If you want to see this image, you have to place a screen here. Unless you cannot see it. Clear? At the same time, the image is enlarged. Inverted image and enlarged image. Enlarged in the sense the size of the image will be greater than that of the object. Clear? Greater than that of the object. This is enlarged. And next, this is a third case. Now let us see in the fourth case. Now what in the fourth case, what we will do is, we will place the object on focal point, right? So when you keep object on focal point, let us see what will happen. Right? It is F2, F1, 2F1, 2F2. Right? Now we are placing here. Now let's place the candle at focal point. Now a light ray passes parallel to principal axis. What will happen? It passes through focal point. And second light ray, this passes through optic center. It's never deviate. Let's observe. Are they meet anywhere? After refraction, are they meeting anywhere? No. How long you extend? Even forward or backward you extend. They are not meeting anywhere. That means an object is placed on focal point. The image will be formed at infinite. Clear? Image will be formed at infinite. So either it is real or virtual, we cannot tell anything. Clear? So when the object is at focal point, the image will be at infinite. So what is image? The point of the converging point of refracted or reflected light rays, right? So they are not meeting anywhere. So image will be formed at infinity. So we cannot tell. Clear? And next, last condition. It's very important. Its applications will be very important in human being life. So let us see. Biconvex F2 and F1. It is 2F1 and it is 2F2. Now the object is placed between optic center. This is optic center and focal point, or else between lens and focal point. The object placed between the lens and focal point. Now let us see a parallel beam of light. It's never, it passes through this, and the second one. Right? Now, are they meeting anywhere? If you extend forward, will they meet anywhere? No, they don't meet anywhere. So you cannot expect image this side. Once you try to extend them back, that means if you extend this refracted ray back side, right, it is moving like this. Okay, and next this is also refracted ray kuda, if you extend them back, yeah, see, the refracted rays are not meeting, but they are appearing like they are meeting at a point, or else they are behaving like they are coming from this point. If we extend them back, then they are behaving like they are meeting at a point. So here the image will be formed. See now. Let me draw here. Right? See now. So is it useful in our daily life? If you observe carefully, this is the object. Up to the distance of, if I would like to tell, when the object distance is greater than focal length, this is the focal length. When the object distance is greater than this focal length, then image used to form here, which is called real image. When the object distance is equal to focal length, you cannot see any image at infinite. When the object distance is less than the focal length, then the image will be formed same side of the object. So if you want to see this image, if you place a screen here, you cannot see. If you want to see this image, you have to see directly through this lens. Keep object here and you watch from the lens directly. Then you will see this enlarged and erect. Up to before, inverted image and real image. But now enlarged, erect and virtual image. To watch or to see the virtual image, we don't need any screen. Directly you can see with your naked eye. Right? So according to the object distance, the nature of the image is changing. Clear? You must remember that. Now enlarged, erect image and virtual image. Clear? So this is what our concept. So you must remember that when the object distance is greater than focal length, then what is happening? The image will be real, inverted and enlarged. Clear? And next, when the object distance is equal to focal length, then image will be formed at infinity. And when the object distance is less than focal length, then virtual image and enlarged, clear? Enlarged and erect image, not inverted. Now can you apply this in our daily life? The entire situation? Yes, we can apply. If you go to the dentist, he will take the biconvex lens. What he will do? Instead of this candle, he will see your tooth. Right? He will see your tooth and it appears very bigger the size. The dentist will use the same lens. Clear? Hope everyone is clear with all these concepts. If you have any doubts, please comment below. Thank you very much. Shining.